Hello everyone, welcome to today's LogiStem Math Club session. So we'll be starting very soon. So today we'll be going through some problems from the 2021 middle school Purple Comet Math Meet. And these problems are pretty interesting. So I'll give you all some time to think about these problems before we move on to some discussion. So I'm gonna post the file in the chat box, and hopefully you guys will be able to see the file. Okay, can everyone see my screen? Yes, okay, cool. So we'll first go over the problems posted in the chat box, which are 3, 4, 6, 9, 13, 15, 16, and 17. And then if time allows, we can check out some others as well. If any of you have any questions during this the discussion, feel free to post them in the chat box also. All right, so let's start with problem 3. So in problem 3, we have in case any of you don't have the problems from before, I'll just repost the problems in the chat. Okay, so for problem 3, we have some conditions that we want to satisfy, and we want to find the greatest and least numbers that satisfy these conditions. So in particular, what we have are two 10-digit numbers that are rearrangements of the digits 0 through 9. So for example, one possible rearrangement you can have is 162847305 In this rearrangement of okay, so this 10-digit number is a rearrangement of the digits 0 through 9. And so what that means is that each of the digits 0 through 9 appear exactly once in this number. And so this is our first condition. Our second condition is that no two adjacent digits are consecutive. So what this means is that we cannot have say 0 and 1 together. We cannot have 2 or 3 together, and etc. So we want to find the greatest and the least possible 10-digit numbers that satisfy these two conditions. So for example, this number is a condition that satisfies both conditions because there are no two adjacent digits that are consecutive, and all the digits appear exactly once. All right, so let's erase this number, and now what we'll try to do is to try to find what the greatest and least 10-digit numbers of this form are. So first, let's try to find what m is, capital M. So for this number, we want to make it as large as possible while still having each of the digits 0 through 9 occur exactly once, and no two digits that are adjacent are also consecutive. So first, if we want to maximize what this big M is, we want to start with the digit 9. Because if we use any other digit like 8, we'll have a smaller number. and we want to find the greatest number. So we'll start with 9. And so now that we know that our first digit is 9, we want to see what the second digit or third digit would be. So let's first look at the second digit. We want to make the second digit also as large as possible. Well, so first, it cannot be 8 because if the second digit is 8, the first two digits, 9 and 8, they are consecutive. And since no two adjacent digits can be consecutive, this is not allowed. So instead, we can make our second digit 7. And so far, we haven't broken any rules yet. All right, so in order to maximize what this number is, we want to maximize the first digit and then the second digit and so on and so forth. So for the third digit, the maximum possible digit that we can choose is 5. Because we cannot repeat any digits, and we also cannot have 8 or 6 in this position because then because 7 and 8 are consecutive, and so are 7 and 6. So our third digit must be 5 if we want to maximize this number. All right. So now, the next digit, for the next digit, we have some more choices. We want to maximize our fourth digit, which can be, it cannot be 9 or 7 or 5, but it can be 8, 6, 4, 3, 2, 1, because those have not been chosen yet. But we can also notice that it cannot be 6 or 4 because those two numbers are consecutive to 5. But it doesn't matter in this case because 8 is the largest number possible, and that is the number we'll choose. So now we repeat the same process. After 8, the largest digit that we can choose for the next digit is 6. And the next one is 4, and then 2. And then now we have something interesting since we have the 3 digits 0, 3, and 1 remaining. If we want to maximize the next digit, we want to choose 0. And then if we want to maximize the next digit after the 0, we have 3. And then after that, we have the digit 1. So this is the greatest number that we could possibly make. And what we can see is that we've maximized this number at every stage that, every step of the way that we tried to construct this number. So we know that this is the maximum because we've basically maximized this number every step of the way. So this is our value for m. All right. So now that we have what our value for big M is, let's find the value of little m. So as for little m, we know that since what we want is a 10-digit number, we cannot start with the digit 0 because 10-digit numbers cannot start with the digit 0. So instead, let's start with the digit 1. And since this time we want to find the minimum possible 10-digit number that satisfies these two conditions, the next digit we want to minimize as well. So we want to minimize the next digit every step of the way. So in this case, our next digit would be 3 because the two smallest digits that we could put here are 0 and 2, and those two digits are both consecutive to 1. So our next digit is 3 if we want to minimize this number. And then, of course, our next digit would be 0 after the 3 because 0 is not consecutive with 3, and it is also the smallest possible number, the smallest possible digit that is not consecutive with 3. And after 3, we would have 2, and after 2, we would have 4. After 4, we would have 6. So every step of the way here, we're finding a next number that is the smallest possible and also not consecutive with the previous number. So after the 6, we would have 8 because the smallest possible number would be 5, and then the next smallest would be 7, and those two are both consecutive with 6. So after the 8, we would have 5, and then 7, and then 9. And what you see here is that we've minimized this number every step of the way. So we know that this number, little m, is the smallest possible rearrangement of all the digits 0 through 9 with no two adjacent digits consecutive. So now we've found the values of big M and little m. And so now we can subtract these and we'll get our answer of 8456173,452. And that's our answer. All right, so are there any questions about this problem? If there aren't any, we can move on to problem 4. All right, it seems that there are no questions, so let's move on. All right, so in problem 4, we have a regular pentagon and a square that is kind of inside this pentagon and shares a side with the pentagon. We want to find the degree measure of FAG, which is this angle. All right, so how can we find this angle? So in order to find this angle, we want to consult some of the angles that we know how to find. So for example, we can notice that this angle is equal to the angle EAB minus the angle EAD, and then minus the angle FAB. And since we know the angle measures of the pentagon, the regular pentagon, as well as the square, each of these angles are pretty easy to compute. So first, angle EAB is just an internal angle of this regular pentagon. And probably so many of you have already memorized this angle to be 108 degrees. But in case you haven't, the way we can find that this is 108 degrees is by noticing that the total of all angles in this pentagon is 180 degrees times 5 minus 2, which is 3. That's the total, that's the sum of all internal angle measures. And now we divide by 5 since all 5 angle measures are the same. So the answer here, or the angle measure here, is 108 degrees. So that's the angle measure of EAB. So now we also want to find what the angle measures of EAD and FAB are. So as for EAD, we can notice that EAD is contained in this isosceles triangle. And in this isosceles triangle, we have angle DEA, which is an internal angle of the pentagon. And we've just seen that this angle is equal to 108 degrees. And then, since this triangle DEA is isosceles, we can find out that EAD, this angle, is 36 degrees. And that's because we're taking 180 minus 108 all over 2, which gives 36 degrees. So angle EAD has measured 36 degrees. And then lastly, we want to find the angle measure of angle FAB. And since AF is the diagonal is a diagonal of this square, we can find out that this angle, FAB, is actually equal to 45 degrees. So now we've found all the angle measures that are necessary for computing angle FAD measure. So now we can finish our calculations and we'll get 27 degrees as our answer. All right, so that's it for problem 4. Are there any questions? If there are no questions, we can move on to problem 6. All right, I haven't got any questions. So let's move on to problem 6. In problem 6, we want to find the least integer n that is greater than 60, so that when 3n is divided by 4, the remainder is 2, and when 4n is divided by 5, the remainder is 1. So one thing we could do here is we see remainders, and we're dividing by numbers, and we have remainders. So one way we can denote this is by using modular arithmetic. So in this problem, we would write 3n is congruent to 2 mod 4. And so what this means exactly is the remainder when 3n is divided by 4 is the same as the remainder when 2 is divided by 4, which is 2. And then we have another congruence. So 4n is congruent to 1 mod 5. All right. So there is a way that we can rewrite these two linear congruences to make it simpler. So we can notice that 3n is congruent to negative n modular 4, mod 4. So we can rewrite our first congruence as negative n is congruent to 2 modular 4. And similarly, we can rewrite our second linear congruence as negative n is congruent to 1 mod 5. So what this means is that negative n gives remainder 2 when divided by 4, and also negative n gives remainder 1 when divided by 5. We can rewrite these as n is congruent to negative 2, which is congruent to 2 mod 4, and n is congruent to negative 1, which is 4 mod 5. All right, so now we have these two conditions on what n can be. So let's find the smallest possible number for which this happens. And so we can check n equals 4 does not work because 4 is congruent to 0 mod 4. 9 does not work either because 9 is odd. And then our next number that we could try is n equals 14. And we see that n equals 14 satisfies these two constraints. And so that means that n is congruent to 14 mod 20 is the unique solution to this system of linear congruences. And this is because of a theorem called the Chinese remainder theorem, which tells us in this case that n congruent to 14 mod 20 is the only possible solution mod 20 to this system of linear congruences. So now what the problem wants us to find is what is the least integer n that's greater than 60 and has a remainder of 14 when divided by 20. And this is a lot simpler, since we can see that the smallest such number is 14 times 20, 14 plus 20 times 3, which is 74. And that is our answer. Oh, okay, so how does modular arithmetic work? So in this problem, we're given a bunch of remainders, and so modular arithmetic is, okay, so in modular arithmetic, we write A is congruent to B, modulo some number n, if and only if n divides A minus B. So in other words, we say that two numbers are congruent modulo n if they share the same remainder when divided by n. So for example, let's just take this as an example. So 3n is congruent to negative n mod 4, because we see that 3 is congruent to negative 1 mod 4, because both 3 and negative 1 give a remainder of 3 when divided by 4. And then we can multiply n to both sides of this equation. 3 is congruent to negative 1 mod 4. Notice that multiplying by an n doesn't change the fact that the remainder, but the fact that the two sides of this linear congruence have the same remainder when divided by 4. So what we've done here is we've said that 3n is congruent to negative n mod 4 because, well, so I guess first of all, 3n minus negative n is a multiple of 4. And also in this case, 3 is congruent to negative 1 mod 4. And we can multiply n to both sides to get this, to get that 3n is congruent to negative n mod 4. All right, so I hope that clarifies things. Okay, so in the remainder of this problem, what we've done is basically we've taken what we have here, and then we've solved these the system of linear congruences by finding out one such number that satisfies both of these linear congruences. And then we can find out that the answer has to be 14 mod 20, which means that it has to give remainder 14 when divided by 20. So then we can find that the smallest such integer that is greater than 60 is 60 plus 14, which is 74. All right, so are there any other questions on this problem? All right, so next, let's move on to problem 9. All right, so in this problem, we have a system of linear equations. Or no, not linear equations. We have a system of equations. So here, we notice that we have these terms, a and negative 100a, negative 100 over a, in both equations. So one thing we could do is we can isolate these two terms on one side of each equation and see what we get. So let's rewrite these equations as a plus 100 over a is equal to 11 plus 12b, and a plus 100 over a is equal to 4 plus 12 over b. And then we notice that the left-hand side of these two rearranged equations are both the same thing. So in this case, what we can do is we can designate this number as a variable x. And then we can notice that x minus 11 is equal to 12b, and x minus 4 is equal to 12 over b. This is just bringing over the constant to the left side on both equations. And then we can multiply these two equations to find an equation just in terms of x. And we can do our expanding. And we can factor this quadratic equation to get x minus 20 times x plus 5 is equal to 0. So this gives x is equal to -5 or 20. But the problem tells us that a and b are both positive real numbers. So since a is a positive real number, so is 100 over a. And this would make a plus 100 over a a positive real number as well. So x is positive, and we can ignore the solution. So now we've gotten that x is equal to 100, or x is equal to 20. And so we have this equation, a plus 100 over a is equal to 20. All right, so now that we have this equation, we can notice that if we multiply both sides by a, we would have a squared minus 20a plus 100. I've also moved the term 20a on the right-hand side to the left-hand side, and we can see that this is a perfect square. So a minus 100, sorry, a minus 10 squared is equal to 0. And this tells us that a is equal to 10. So now we've found what a is, what the value of a is. And that is great progress, because now that we have what the value of a is, we can find what the value of b is. In fact, since we already know what x is, we can simply plug it into this equation over here. So we'd have x is equal to 11 plus 12b. And since x is equal to 20, that would mean that 9 is equal to 12b. And so b is equal to 3/4. So now we've calculated both a and b. And so we can find what a plus b is. And in this problem, we have a plus b is equal to 10 plus 3/4, which is 43/4. And what we want to find is m plus n, which is 47. So that's our final answer. Okay, any questions? Okay, if there are no questions, let's move on to problem 13. Okay, so in problem 13, we're asked to find the greatest prime number p such that p cubed divides this number. So when you first see this number that they give you, you can notice that we have some very high factorials. So maybe there's something we could do with these factorials to factor this number nicely. So this first term, 122 factorial over 121, we can rewrite this as 122 times 120 factorial, because what we have here is 122 factorial, but 121 is missing. So what we have then is 122 and 121 is missing, and then we would have 120 factorial. So this is what we get when we rewrite the first term of this number. So let's write, let's rewrite this expression on the side here. And let's see what we can do with it. So now we've rewritten the first term of the expression. Let's try to rewrite the second term now. So the second term, 123 factorial, we can rewrite this as 120 factorial times 121 times 122 times 123. But in this case, we're going to write it in this form. We're going to write 122 first, because we can notice that this number, 120 factorial times 122, can be factored out of both terms. And so, after we factor this out, we would have this number, 120 factorial times 122 times, in parentheses, 1 plus 121 times 123. And then what's interesting here is we can rewrite 121 times 123 as a difference of squares. And this is equal to 122 squared minus 1, which is super nice because we have a plus 1 behind this number. So in fact, what we're left with is 120 factorial times 122 cubed. And so now we can notice that we basically have somewhat a prime factorization of this number, because technically we can factor 120 factorial as whatever that thing is, but we notice that we want to find the greatest prime number p such that p cubed divides this number. And looking at the board right now, the greatest prime number that divides this number that I can see directly is 61. So what remains is to ask yourself, is 61 the answer? So in other words, we want to check if there is a greater prime number such that p cubed divides this number. So is there a prime greater than 61 that divides this number 3 times? And the answer here is no. Oh, how does it become a sum of squares? So after we factored out the 120 factorial times 122, we have 1 plus 121 times 123. And we can rewrite 121 as 122 minus 1, and we can rewrite 123 as 122 plus 1. And the reason we do this is to take advantage of difference of squares, because we know that x minus y times x plus y is equal to x squared minus y squared. And in this case, we would have 122 squared minus 1 squared, which gives 122 squared minus 1. And we see that this gives a super nice factorization of our number. All right, so now what we have left to do is to check if there are any primes greater than 61 that appear 3 times inside this number. And we notice that if there is a prime greater than 61 that appears in this number 3 times, it cannot appear anywhere here, because in this part we have only factors of 2 and 61. So we cannot have any factors of any prime greater than 61. All prime factors that are greater than 61 must appear in this term, in this factor of our number. And then we can notice that any prime that is greater than 61 will appear at most or exactly once, at most once, because there's some very large primes that don't, primes that are greater than 120 do not obviously do not divide this number. But for any prime that we want to consider that divides, that's greater than 61, we can notice that this number that we have here can divide it at most once. Because, for example, if we have 67, we cannot have two factors of 67 inside 120 factorial, because that would require us to have a term for 67 and a term for 134 at the very least. So now we've proven that the greatest possible prime number p such that p cubed divides this number is 61. And so that is our answer. All right. Any questions? Okay. If there are no questions, we can move on to problem 15. All right, let's move on to problem 15. In problem 15, I'm going to introduce to you a very interesting factorization of an expression. So some of you might already know this, but we can factor x cubed plus y cubed minus z cubed minus 3xyz. Sorry, that's 3xyz is equal to x plus y plus z times, or let's write a half times x plus y plus z times x minus y squared plus y minus z squared times plus z minus x squared. So this factorization will come in handy when we've done some manipulations to this equation over here. So let's start. In this equation, we have a bunch of stuff that are in parentheses. And the parentheses don't really help us with doing anything in the problem, so we might as well get rid of them. So instead of keeping all of the terms in parentheses, let's directly expand. So we'd have m cubed n cubed minus 27 m cubed 27 m cubed minus 27 n cubed plus 729 is equal to 27 m squared n squared plus 729. So now we can see that these two terms can get canceled out. And once we cancel out these terms, we notice that these three terms, they're all perfect cubes. And that makes us think of this identity we have here. So let's try to write it in that format. So let's write mn all cubed plus negative 3m all cubed plus negative 3n all cubed, and then minus 27m squared n squared is equal to 0. And since we want to write it in this format, we want to see what 3 times mn times negative 3 times negative 3m times negative 3n is. So we can notice that we can further rewrite this equation as our last term. We can rewrite it as 3 times mn times negative 3m times negative 3n. And now we have an equation that is exactly in the form described up here. So here, let's substitute the variables x, y, z for these three numbers. So we would have exactly x cubed plus y cubed plus z cubed minus 3xyz is equal to 0. And we can consult this factorization. to get that a half times x plus y plus z times x minus y times x minus y squared plus y minus z squared plus z minus x squared equals 0. And so in order for this thing to be 0, one of our two non-constant factors must be 0. So we have two cases. Our first case is if x plus y plus z is 0. And we see that this means that if we substitute back our numbers that x, y, and z represent back into this equation, we would have mn minus 3m minus 3n is equal to 0. And then we can add 9 to both sides, and we would get this, on which we can apply Simon's favorite factoring trick. So we'd have n minus 3 times n minus 3 is equal to 9. So now we can see that m and n, m minus 3 and m minus 3 must be either 1 and 9, 3 and 3, or 9 and 1. So we can see that m and n are either 4 and 12 or 6 and 6 in some order. So let's write the pair m and n is equal to either 4 and 12 or 6 and 6. So in these two cases, we can see that m cubed plus n cubed is equal to either 12 cubed plus 4 cubed, which is 1728 plus 64, which is 1792. And then, or it can be 6 cubed plus 6 cubed, which is 432. All right, so these are two possible values of m cubed plus n cubed, and these are the only two possible values of m cubed plus n cubed in this case. So now let's explore the second case. That is if this thing is equal to 0. And here we can notice that a sum of squares can be equal to 0 only if each of the terms inside the squares are 0. So this means that x minus y must be 0, y minus z must be 0, and z minus x must be 0. So in fact, x equals y equals z. And then we can see that since x equals y, mn is equal to negative 3m. And this forces n equals negative 3 or m equals 0. And this is impossible since m and n must both be positive integers as given in the problem. So this case is impossible. So now we found that the only possible values of m cubed plus n cubed are 1792 and 432. And the larger of these two is 1792. So that is the answer. All right, any questions? Okay, so I haven't gotten any questions, so let's move on to
the chat.
Huh? I'm sorry?
Can you write the formula in the chat and explain why you got it?
Oh, sure. So the formula is x cubed plus y cubed plus z cubed minus 3xyz is equal to a half times x plus y plus z times x minus y all squared plus y minus z all squared plus z minus x all squared. And this is a useful factorization of this this expression because this expression has a sum of cubes in it. And so when we see a sum of cubes, we can resort to this equation, this identity, to write it in terms of simpler terms. So In fact, this right-hand side we can rewrite as x plus y plus c times x squared plus y squared plus z squared plus xy plus yz plus cx. And this is an interesting factorization of x cubed plus y cubed plus z cubed minus 3xyz that comes in handy once in a while. Oops. All right, so if there are no more questions for problem 15, we can move on to problem 16, which is an exercise on casework. All right, let's move on. So problem 16 tells us to find the number of distinguishable groupings into which you can place 3 indistinguishable red balls and 3 indistinguishable blue balls. So we have 3 red balls, R, R, and R. You can't tell apart what they are. And also we have 3 blue balls as well. So we want to group these balls into indistinguishable groups, and we want to find find the number of total ways we can do this. So here, what we're going to do is we're going to perform casework on the number of balls in each group. So like we can call this the group partition. So for example, one possible partition is just have one group with all 6 balls in it. And there's only one way this can happen. Another possibility is if there is 5 balls in one group and 1 ball in the other. And for the group that has only 1 ball, there are exactly 2 ways to choose what color ball is inside this group. So in this case, there are 2 possibilities. And then we can do this for every possible partition. Our next partition is 4 plus 2. And the number of ways we can partition the 6 balls in this way is basically the number of ways we can choose the 2 balls in the group with 2 balls in it. And it can be either 2 blue balls, 1 red and 1 blue, or 2 reds. And these are the only ones because here we're considering RB to be the same as BR because they both mean that this group has 1 red ball and 1 blue ball. And we don't have to order the different balls in a group. So these are the only possibilities. And then we have our next partition, which is 4 plus 1 plus 1. In 4 plus 1 plus 1, we have basically the same idea. We choose the balls, we choose the colors of the balls in the 2 groups with size 1. And we can see that 3 possibilities are shown here. Again, having 2 groups with red and blue would be the same as having 2 groups with 1 blue and 1 red. And this is because we would be merely rearranging the groupings. So here, in this case, we would still have 3 possible distinguishable groupings. And then we can go on to our next case, which is 3 plus 3. here, we want to divide these 6 balls into 2 groups of 3, such that there are totally 3 red balls and 3 blue balls. So the ways we can do this are either having 2 groups, one with 3 red balls and one with 3 blue balls, or we could have 2 groups, one with 2 red balls and 1 blue ball, and the other having 2 blue balls and 1 red ball. And we can see that these 2 are the only 2 possibilities, because all other possibilities are merely rearrangements of this grouping, of these 2 groupings. So in this case, there are only 2 possibilities of our grouping. Our next case is having one group with size 3, one group with size 2, and one group with size 1. So as for this one, we can first choose the color of the ball in the group with one ball in it. And there are 2 ways to do this. We can choose either red or blue for this group. And then if we choose blue, for example, we would have the same thing if we choose red. But if we choose blue, we would have 2 blue balls remaining and 3 red balls remaining to put into the group, to put into the 2 remaining groups. And the number of ways we can put the remaining balls into the 2 groups is 3, because we want to choose 2 balls to put into the group with 2 balls in it, and the remainder of the balls will go into the group with 3 balls in it. So the answer is 6 in this case. And then our 7th case is if we have 3 plus 1 plus 1 plus 1. So this would mean we have 3 groups of just 1 ball each. And once we determine what the balls are in these 3 groups, we've determined the entire grouping. Since the last group with 3 balls in it would be just the group with the remaining 3 balls. So we can list out the possibilities. We can have 3 groups of 1 ball each, 2 groups of 1 ball each, 3 groups of 1 blue ball each. We could have 2 groups of 1 blue ball each, and 1 group of 1 red ball. Or we could have 2 groups of 2 red balls each, and 1 group with 1 blue ball. Or we could have all three of these 1 ball groups having red balls. So the possibilities are shown here. And any rearrangements of this give the same thing, because it would be a rearrangement and those are not counted twice. So in this case, there are exactly 4 possible things. And then we have the case when we have 3 groups of size 2. And the possibilities in this case, you can see, are only having 2 blue balls in the first group, 2 blue balls in a group, 2 red balls in a group, and then 1 blue and 1 red in the last group. Or we can have 1 blue and 1 red in all 3 groups. So there are 2 possibilities for the number of groupings in this case. And then next case, we could have 2 plus 2 plus 1 plus 1. In this case, we can choose what the 2 groups with 2 balls are first, and then the last 2 groups, each with 1 ball, are fixed, given what we choose on the first 2 groups. So we can list out all possibilities here. So we could have RRBB, which would be the same thing as BBRR, because those are rearrangements of each other. We could also have RB, RB, or BB, RB, or RR, RB. And these are the only 4 possibilities. So in this case, we would have 4 again. And our second to last case is if we have 1 group with size 2 and then 4 groups size 1. And in this case, we can see that we can just decide which two balls, which two colors go into the ball, go into the group with two balls in it, and we can see that the three possibilities here are having red red, red blue, or blue blue, and then the four other groups are determined up to rearrangement based on what two balls we put in the first group. So for example, if we put red red in the first group, the remaining four groups must be red blue blue blue, and one ball each. So in this case, we have three balls, three groupings again. And last but not least, we have our grouping or partition with one ball in each group. And for this one, there's only one way, because we would just have three groups with one red ball each and three groups with one blue ball each. And there are no other possible groupings up to rearrangement. So once we sum up all of these cases, we find that the answer is 31. All right, any questions? Okay, so it seems we're going a bit over time, so y'all may leave now if you want to, but we can also go over one more problem, problem 17, before ending this session. So are there any questions on this problem before we move on to our final problem of the day, which is problem 17? All right, let's move on to problem 17. So 17 is a geometry problem. So we have a triangle. Let's try it. Okay, so we have this triangle. Let's actually put C on top so it's easier to draw. So at points X and Y lie on side AB of this triangle. And we're given that AX is equal to 20, AY is equal to 28, and AB is equal to 42. So we can write AX is equal to 20, XY is equal to 8, and YB is equal to 14. And then we're given that CX is equal to 26 and CY is equal to 30. So let's draw out CX and CY. All right, let's try to draw this somewhat accurately. All right, so now we've drawn out CX and CY, which have lengths 26 and 30. And we want to find AC plus BC. So one thing we can do here is we can drop an altitude from C to AB. And let's let the height be h and the distance from the foot to x, we can let this be d. And then the distance from the foot to A would be 20 minus c. And so we know cx and cy, so we can create some Pythagorean equations with these numbers. So for instance, in right triangles C, let's call this D. In right triangle CDX, applying Pythagorean theorem to this right triangle gives us that h squared plus d squared is equal to 26 squared. And then applying Pythagorean theorem to triangle CGY, which is also a right triangle, we can get that h squared plus d plus 8 squared is equal to 900. And so now we see that if we subtract these two equations, we'll get rid of h, and then we can find what d is. So let's do that. If we subtract these two equations, we get that d plus 8 all squared minus d squared is equal to 900 minus 676, which is equal to 224. And then we can expand out what this number is, and we see that this is equal to 16d plus 64. And once we move 64 to the other side and then divide by 16, we get that d is equal to 10. So now we've solved for d, and we want to find AC plus BC. And we see that now that we have d is equal to 10, we see that also this length AD is equal to 10. So we've found both AD and DB, which is 10 plus 8 plus 14, which is 32. So all we have to do to find AC and BC is to find the value of each, which is the height. So let's do exactly that. Using this equation, h squared plus 10 squared is equal to 676, which is 26 squared. We can find that h is equal to 24. And so once we have h is equal to 24, we can find exactly what AC and BC are, and then we can sum them. AC is equal to 26 because we have this right triangle ACD with legs of length 10 and 24. We can also find BC to be 40 because the legs of right triangle CGB are of length 24 and 32. So we've now found what AC and BC are. They are 26 and 40 respectively, and summing the two gives the answer of 66. So that's our final answer of the day. Are there any questions before we end the session?
Wait, so are these triangles congruent or no?
Are triangles CAD and CGX congruent?
Yeah.
Oh, how do you know that? Oh, sorry, there's another question. So here, it's not really necessary to find any congruent triangles because all we're doing here is we're taking an altitude from C to AB, and we're using Pythagorean theorem and finding some equations to find out some lengths. All right, so there's another question. How do you know angle CXY is obtuse? All right, so I think it's probably also possible for CXY to be acute. Based on the way I drew this diagram over here, it makes sense for angle CXY to be obtuse. But I guess technically there might be another way we can draw this diagram, which makes CXY acute. And in this case, let me try to draw it over here. So we would have a triangle like this. And we would have x on this side and y on this side. Or if we have CXY acute, what that would mean is that we would have something like this instead. ACB and here we have x over here with the 26 and y over there with length 30. We would have something like this. And this would make, again, we would still have ax is equal to 20, xy is equal to 8, and yb is equal to 14. All right, this is interesting. So let's try to solve the same problem, but with this configuration instead. So if we have this configuration, we can drop the height, we can drop the altitude from C to AB as we did before. And then let's call this point D. And then let's let d x have length lowercase d again. And then here we can see that dy has length d minus y, or dy has length h minus d. And then we can write our equations d squared plus 64, d squared plus h squared, not 64, is equal to 676, and d squared, or rather h minus d squared, plus h squared is equal to 900. And we can subtract these two equations as we did before to find 16d minus 64 is equal to 224. And here what we get is d is equal to 18. Yeah, 18. So then that would mean that dx is 18 while xy is 8. And in this case, this is impossible because we cannot have a part of this. We cannot have a part of a segment that is that has a longer length than the segment itself. So what this would mean actually is that this configuration is impossible. So I guess trying to draw a somewhat accurate diagram can help you see whether it's possible, or whether it's possible for this angle to be acute or obtuse. And then if you do the calculations, you can see that if we have angle CXY acute, it's actually not possible to create such a triangle. Okay, so I hope that answers your questions. All right. All right. So if there are no more questions, we can end this session here. Thank you all for attending today, and hope to see you all in our next session, whenever it is.
What is your email?
Oh, I can send the Logistem email in the chat in case any of you have any questions about these problems. If you have any questions about anything, you can email the Logistem Math Club. We just post this email real quick. All right. Okay, so thank you all for, oh, I did not send it. Here is the email. If any of you have any questions, feel free to send anything to this email account, and we'll be checking it regularly.
Okay.
Yeah. All right, so thank you all for joining. And that'll be the end of today's session, today's Purple Comet discussion session.
Thank you.
Right.
Bye.
Bye, everyone.
Bye. Thank you.